and it's little more difficult to perform and could be potentially a little more expensive. But that's what we'll talk about today, is this UU triaxial test. I'm looking here at Canvas, and we have a new module set up for the triaxial test. And first I'm going to, we'll revisit this, the report requirements and the data and so on. But first I'm going to give you a little background about triaxial test. So this test is performed in a triaxial cell, and if you watch the video that shows the test setup, you'll have a good idea of what the triaxial cell looks like, and I would recommend watching that video and then coming back to this one and maybe going back and forth between the two, and together they will provide a pretty complete picture of this test. So for first, I'm going to start off with just a sketch of a cylindrical specimen that would look something like this, just a section. And it's placed in a cell, and that cell is filled with water. And I know this may not make a lot of sense, every kind of detail I'm explaining right now, but if you watch the other video and then come back to this, it'll all be very clear. So this is the sample. It's placed in the cell. The cell is filled up with water, and that water is pressurized. So the sample is isolated from the cell because there's a membrane that's around it, around the soil itself. And then the cell is filled with water, and it's pressurized. That water is pressurized, and we get to increase the pressure to some specified value that we call the confining pressure. And it acts all around the sample. So it's all over. And we call that value sigma 3. So this is the stresses are acting in 3 axes on this one, because I just have the section here, but there's water pressure acting on the back side and the front side and all around this sample. So this is the first kind of phase for this test, is applying this confining stress all around the sample. And the reason for that would be to model the stresses the soil is going to feel in the ground when it's loaded. So that's what this is the method that we can use to kind of model the field stresses, is using this water pressure. So this is the first phase of the test, kind of like when we put the normal stress on the direct shear sample. This is kind of similar to that. So this would be the consolidation phase. So this first step would be the consolidation phase. One little twist here. This would be the consolidation phase. There's plumbing, there's valves and tubes that are hooked up to this sample. So we could allow, when we put this stress on the sample, if this is a saturated sample, we could allow water to drain out. We could call that consolidation. This test this particular version of the test that we're doing, of this triaxial test, is actually, we're not going to allow any consolidation to occur when we apply the confinement. So triaxial test, there's several different versions. I'm not going to go through all the different versions today, because they're going to be discussed in lecture. I'm just going to talk about a particular one called the unconsolidated undrained test. So this is what could be the consolidation phase, but for this particular test, we are not going to allow any drainage to occur from the sample. So any valves that connect to the sample are going to remain closed, and we're not going to allow any consolidation. So what we're doing is, for this phase, it's unconsolidated. So we're not going to allow any water to drain out. Of cell pressures, this is also called, here we had a kind of peak value, and that was the highest stress we were able to withstand for this soil. And so this value right here, that would be our delta sigma at failure. That's what this is. I'm just going to put a subscript F there for failure. Okay, so that's delta sigma at failure. And so now with this value, you're going to make this plot, by the way. Okay, and you're going to assess the strain at failure. This would be the strain at failure. and delta sigma at failure. Okay, so now if we go back and look at this shearing phase, at failure we have our sigma 3 at failure. That doesn't change throughout the test, so that's not too exciting, it's the same. And then we have our delta sigma at failure. So we can look, we're looking at the stresses on principal planes here, right? So principal planes would be planes that had zero shear stress. So on this vertical plane, this is a principal plane. The shear stress, the normal stress is sigma 3. And on this horizontal plane, another principal plane, the normal stress at failure would be our sigma 3 plus our delta sigma at failure. So I'm going to just draw another diagram here. And on our principal planes at failure, we have our sigma 3. I'm going to write, I could write at failure, but it doesn't change, so I'm not going to do that. And then we have, that acts all around. We don't change that. That's that from the water pressure. And then we have on top of that, when it finally fails, we have our delta sigma at failure on these. Oops. Right? Oh, I'm sorry about that. So this is the condition at failure here. So we're interested in failure. At failure, we call the sum of delta sigma 3, sigma 3 and delta sigma, we call that value sigma 1. So sigma 1, this, if we're looking at the condition at failure like we are in this, which would be when we had our peak delta sigma, we could call this delta 1 or sigma 1 at failure. And that's the convention here for naming the stresses. So at failure on our principal planes, we have sigma 1 at failure and sigma 3 at failure, or sigma 3 because it doesn't change, so it's the same thing. So if we know the stresses on the principal planes, we can draw a Moore's circle, right? We can easily do that. Okay, so we have a minor principal stress and a major principal stress. The lower one is the minor one, that's sigma 3. The greater one is the major one, that's sigma 1. And we're specifically just interested in this condition at failure. So now the next thing we're going to do is construct that Moore's circle. So Moore's circle, we're looking at tau sigma space here, so stress, shear stress, normal stress space. And when you create your Moore's circle, make sure you have the same scale, a true scale. So if this physical dimension, whatever, between my fingers, let's say that is 1 KSF, then this distance, however you set this up, needs to be 1 KSF over here. Okay. So make sure you construct that. That way when you make the circle, it looks like a circle. Otherwise, it'll be exaggerated in one direction. It won't be correct. All right. So we're interested in the condition at failure, and we're going to plot our principal stresses and create a Moore's circle. So our minor principal stress was sigma 3. I'm just going to plot that. So this would represent sigma 3 at failure, which is sigma 3, it doesn't change. And then we added additional stress, normal stress, all the way up. We added delta sigma until it failed. Let's just say it was here. And we added our delta sigma at failure to our sigma 3. And then we had our sigma 1 at failure. So of course the distance on the normal stress axis between these 2 points is our delta sigma at failure. Right, that's That's the distance. So now we have our two principal stresses, and we can create more circles. So I'm going to try to do that, freehand it here. Of course, you wouldn't freehand it. You'll do this in Excel. Pardon my left-handedness. Okay, it's not the greatest, but it'll work. So that's supposed to be a half a circle. So what's the maximum shear stress or strength? Well, it's the peak of this over here, isn't it? It's this value up here. So for this test, our shear strength is this value right here, and we call that, since this is this version of the test we're doing is called the unconsolidated undrained test. We call this value SU, and it's known as the undrained shear strength. Okay, you can relate the undrained shear strength to consistency descriptors. There's tables in Holton, Kovacs, and Sheehan that do that. So when you describe the consistency of fine-grained soil, you can call it soft or stiff or medium stiff or very stiff or hard. All those consistency descriptors are associated with different undrained shear strengths. So they have a specific meaning, all those values, or those words. Okay, so that would be the undrained shear strength for this UU test. And I'm going to revisit this previous set of notes. I said this was unconsolidated during the consolidation phase. I know it sounds kind of funny, but all it means is we didn't allow any water to get squeezed out of the sample. During the shearing phase, again, we don't allow any water to come out of the sample. So during the shearing phase, we call it undrained. There's different versions of this test where you may have, so that means that any valves that are connected to the sample are closed for both phases. There's different versions of this test where you might have the valves open or closed for one phase or the other to model certain types of soil will behave if the loading, if it's a clay type of soil and it's loaded, clay has a very low permeability, so it's not going to drain very quickly, so it will behave in an undrained fashion. Maybe over the years, depending on how thick the clay is and what its drainage path, where it can actually drain, the distance that the water has to travel to where it can actually drain to atmospheric condition. That is going to affect how long it will take to drain. So maybe down the road it will be in a drained condition, but when it's initially loaded, if you have a clay soil, it's going to be undrained. Okay, so that has implications on the strength and the pore pressures that are developed. So we're not getting into development of the pressure within the pores during the draining. That's going to be discussed in lecture. It's more complicated, and it's going to require, several hours and examples and so on. But, it's going to be a more in-depth discussion. But for this particular test, we're doing something that's called, for the shearing, it's undrained, which means the valves are closed here and no drainage can occur. So for this type of testing is associated with clay soils. So when we do a UU test, I'm going to write this on the next page just because this one's getting kind of crowded. So this UU test, unconsolidated, undrained, is associated with clay soil that's close to basically 100% saturated. That is the soil condition that you would typically you would be likely to run or perform a UU test if you have this type of scenario. Okay, so let's take a look at the report requirements. So I'm going to go back to over here to Canvas. We're going to look at the letter report. We're going to look at the report requirements here. Okay. So this is going to be a letter style report. Our load frame is computer controlled. It has electronic data acquisition. The other video will show you the test setup and show you the load frame. You're going to acquire force. So this is the load that's applied. So you'll use the force measurement to calculate the deviator stress. You'll be given pressure. So that's the confining pressure, also known as sigma 3. And you're going to be given displacement data. With the initial height and the displacement data, you can calculate the strain. With the strain, you can calculate the corrected area. With the force and the corrected area, you can calculate the deviator stress that we're applying on that horizontal plane on the top planes on the top and bottom of the sample. I'm going to provide that to you. So you're going to get this in Excel. We'll look at that in a minute. You're going to make a letter report. It's going to be an individual report, and this is what you need to have in your report. So have a table with the soil classification, dry unit weight, moisture content, void ratio, and saturation level. And include the confining stress as well. Confining stress is sigma 3. We're just doing one specimen here, so just one specimen. Base your classification on visual observations, moisture content, dry unit weight of typical values. So you can look in your textbook and maybe other sources. You're going to calculate the moisture content, dry unit weight, void ratio. You can use your values, compare them to typical values, and see if you can classify the soil. You'll also have some images of the actual sample we'll look at in a minute. Include a summary table with classification, undrained shear strength. So that's the SU value that we looked at. That would, of course, the undrained shear strength, I'm going to go back to my notes here. Here's the deviator stress. That's the diameter of the Mohr circle. The undrained shear strength happens to be the radius of the Mohr circle. So in this case, the undrained shear strength is going to be half of the deviator stress at failure. Yeah. Include a summary table with the classification, undrained shear strength, strain at peak deviator stress, and consistency. So based on your undrained shear strength, you are going to describe the consistency by consulting the textbook to pick the correct consistency that's within the range of the undrained shear strength that you measure. Include a failure envelope figure, Mohr circle, indicate undrained shear strength on the figure, confirm the shear stress and normal stresses are using the same scale to produce a circle. So I talked about that already. And then you'll have a short discussion. What's the purpose of the confining stress? Explain that and provide an example. If this test was allowed to consolidate when the confining stress was applied, so what they're asking there is, this is the first phase here. We didn't allow any drainage to occur, but let's say we did. So if the valves that are connected to this were open and we applied the confining stress and some water was actually squeezed out of the sample, that's what they're asking, that's what they're indicating. If that was the case, let's go back. Would the measured strength be higher, lower, or the same as the unconsolidated test we performed? Explain and provide an example. The purpose for this question is for you to have a moment to think about what would happen to the sample and how that would affect its strength if it's allowed to consolidate. So, and so you can kind of think that through. Attached data sheet and example calculation, cite your sources using the ASCE style, create a reference list. Okay, so those are the requirements. And let's have a look now at the data. Oh, excuse me. Before we do that, there's a little more to this. So here we have some of the sample data. So you classify the soil. Table 2 provides the specific gravity, which you'll need to calculate the void ratio. You have the initial diameter, the initial height. You have the mass of the entire sample. So this is just the moist mass of the entire sample. And then when we trimmed up the sample, we took a portion of the material and measured its moisture content. So the tray that we put the soil in to measure the moisture content weighed, this is the mass of the tray. The soil with the tray with the moist soil weighed this. After we oven dried it, it weighed this. So these last 3 columns you can use to calculate the moisture content. This sample mass is the mass of the whole sample that we tested. So you'll have the sample mass, you'll use these to calculate the moisture content. You have the specific gravity, then you can calculate dry unit weights and void ratios. And you're also going to calculate the degree of saturation, and you can do that with the data there. This next table provides an example of the headers that you're going to create, the headers across here that you're going to create to evaluate the data for this report. You're going to be given a column of confining stress. We also call that sigma 3. You're going to be given a column of deviator load, not deviator stress, but deviator load, and you'll be given those displacements or the deflection. With the deflections, you're going to calculate the strains. With the strain, so this is the vertical strain. With the vertical strain, you're going to calculate the corrected area because the sample is going to bulge, and we have to account for that. And with that corrected area, you're going to calculate with the corrected area and the deviator load, you're going to calculate the deviator stress. Okay. And what does the sample look like? So our particular sample, after we've tested it, I took it out of the membrane and took a photo of it, and this is what it looked like. Then I cut this sample in half, so you can see what the inside looks like. This is what it looks like. Okay. Now we're going to have a look at the actual measurements. So this is in Excel, so we'll have a look at this. So these are the data. You have the load that's applied. We could call it the deviator load. This is the cell pressure is the same as the confining pressure. We call it sigma 3. And this should be basically constant. So the only time we use this value is when we are making our Mohr circle. So you could take an average of all these readings for that. Vertical displacement, okay, you have the initial height. This is the change in height. So with these data, you're going to, of course, calculate the strain. So data's pretty straightforward, I think. Report requirements. I think we've covered those. It's an individual letter report, and I hope this discussion will provide you everything the knowledge that you need to evaluate the data and learn something about the unconsolidated, undrained triaxial test.